Hello, this is Mike, and welcome to another Autodesk Inventor Nastran validation. This is the fourth one that I'm recording in the series, and today we're going to take a look at a rectangular plate with all edges simply supported and uniform pressure. It does come from Rourke and Young, Formulas for Stress and Strain, 1975, which is the fifth edition, page 387, table 26, case 1C. And we're going to do edges that are simply supported and a uniform pressure over a central rectangular area. So the pressure will be 100 psi. The plate itself is 20 inch by 10 inch. The loaded area in the center will be 8 inch by 4 inch. The thickness of the plate is a half of an inch. Modulus and Poissons are 30E6 and 0.3 respectively. And we're looking for a max stress of 11,264. So let's take a look at our geometry. I've already constructed it, so if we do a measure, you can see there's a 20 inch by 10 inch rectangle. Basically what I did was I created the sketch of that 20 inch by 10 inch, and then I created 8 inch by 4 inch rectangle so that basically I had a hole in the middle of my sketch, and then I used a patch command in order to create that. So there's the patch command right there, and you can fill in a rectangular region or circular region, etc. And then I just created another sketch right in the middle that is 8 inch by 4 inch. And then again, I patched that. So I basically have two different patches here. And that is one of the ways with surface geometry and Inventor to ultimately end up with shells or plate elements within the Nastran program. And I'll show you an alternate technique for creating the geometry here in the end. So let's go ahead and move this model into the Nastran workspace. I'm going to go from the Environments tab and select Autodesk Inventor. And because we are coming into Inventor without any solid geometry, it doesn't automatically create any idealization for me that would then be utilized for the setup. So I have to create my own idealization. So I'm going to go ahead and click on idealization, and Windows coming up on the other screen because I last worked off of a different monitor. But anyway, idealizations. And in the idealizations, we're going to tell it that these are going to be shell elements, and then we can define what our thickness is. And again, that thickness was 0.5 inch. There are advanced options that you can get into for the shells. We're just going to use the defaults for this example. It'll work fine. We do need to define the material. So let's go ahead and select the new material or tell it new material. Density I'm not worried about. We're not doing anything with acceleration or gravity. The modulus is 30E6, and Poissons in this case is going to be 0.3. And we can give it a name if we would like, just to know that we defined it. So it's verification 4. So I'm just going to call it V4mat, just so I know that I defined it. We can see that's there. Now you could say click on associated geometry and select those two regions. If I leave it unchecked, then it will apply this same material to all the different bodies in my model. So I'll just leave it unchecked for now. With the shells, you do get to decide whether you want to have quadrilateral elements or triangular elements. I'm going to leave it on four-sided quadrilateral elements. We'll say OK to that. So when I say OK, now I have my idealization there. I can see that we have the shell element, and again, that's thickness. And then below that, you can see there is our material. So just to test that everything kind of is working out good so far, let's go ahead and go to our mesh. So I'm going to go mesh settings, and I don't know, we'll start with about a 1/2 inch mesh and see what that looks like. It does not need to be a parabolic or higher element order when we're using shells. I am going to turn on continuous meshing because I'm going to have shell elements in the middle here, shell elements around the perimeter, and I want their nodes to match up so that I don't have to use something like any sort of contact with it. So let's go ahead and say generate mesh, and there we go. We can see the mesh looks pretty good, I think, and the mesh lines up around the perimeter there. So we'll go ahead and and go with that, at least for our initial run. And if we see that we need to refine it, we certainly can, but I think that should be good. All right, so we have the element type, we have the material defined, we have our mesh. We do need constraints and loads. So for the constraints on this one, I'm going to define these as the short edge and the long edge. So I'm just going to assign a name, short edge, and we could make it short edge constraints. And let's go ahead and select our entities, that edge there, this edge here. So the two short edges of the rectangle. And we want to give it some very basic constraints here. So I'm going to go ahead first and say free, so it deselects everything. And we want to stop the vertical movement, so that would be ty. And then whatever the normal direction is to that edge, so let's say tz. So that's all we need for those two edges. I'm going to click the little glasses icon so I can see my constraints that are applied, and I can increase the density if we want. So you'll notice when you don't fully fix the constraints, you can kind of make sense of what the glyphs are indicating. So the vertical one here is indicating that we're constraining the ty direction, and then I have another one that's pointing along the z-axis. So just by looking at those constraints, we know that we have a ty constraint here and a tz. If we do a rotation, rotation is kind of a double arrow. So that's what the rotation ones would look like. Maybe if I put a different one on, you can see it a little better. There you go. So we're not doing anything with rotation constraints, just ty and tz on those short edges. And again, that's for my model's orientation. If you are trying to replicate this and you have your model sketched in some different plane, then of course, constrain it appropriately. What you want to do is the vertical direction or normal to the shells, and then whatever is the axis perpendicular to that edge. Let's go ahead and say OK to that one and make sure that we have our constraints. Yep, there's our short edge constraints. And then we'll do the long edge constraints. I should have made that plural. It's edges, technically. Again, let's make it free. I'll select my edges, that edge right there, that edge right there. And I need to constrain, again, the out of plane, and then in this case, the X direction. And that should be sufficient. Let's turn on the glasses icon, maybe increase our density a little bit. There we go. The density doesn't have anything to do with it. It's just to make it clearer for you when you're looking at the model. So you can change that density wherever you like. You can also adjust the color here. I'm not going to bother with it, but you could certainly go into the color palette if you want to change the color of your constraints or your loads to your liking. Okay, so now we have our constraints. I think the last thing that we need to do would be the load, and the load is going to be a pressure. So let's change that to pressure. The entities, that's the whole reason that we broke out that model back in Inventor into two regions, so that I could select this inner region. If I had just drawn a giant rectangle, obviously it would be much more difficult or impossible for me to select that 8-inch by 4-inch region. So I created those two surface patches back in Inventor, so that way I can select just the one face here where we want the pressure to be. And the pressure in this case is going to be 100 psi. And we'll say OK. And there it is. So it kind of looks like a force. Didn't give my pressure any name. Let's edit it. We'll give it a name just for the heck of it. And we can increase the density of that if we want, just so we can see that it's actually distributed over that area. There we go. And you can adjust the size, make them larger and smaller, and so on. Okay, so let's say OK to that. At that point, we should be ready to run this model. Let's go ahead and run. Given that they are shell elements, there's not a whole lot of them in this model. We're not using the higher order elements. This should go nice and quick, which it does. So by default, it's going to show me the shell von Mises. We need to look at one of the normals here. So there we have a value of 10,000. Let's look at the Y direction. There we go. 11,476 and 11,476 depending on tension or compression. So that's what we're going to take a look at. That is what we're going to plug into our spreadsheet and find out what our difference is. 11,476. And if I hit enter, there you can see the percent difference from theory is 1.88. So really good for this model. I'm happy to see that that all worked out. Now, two other things. First of all, there is some information that I'm leaving out about shell orientation. You can orient these shells to define what their X direction and Y direction is. That isn't necessarily with shell elements aligned to the global X and the global Y. It's more of a local X and local Y in the plane of these shell elements. We just know that we're looking for a value around 11,264, so we could figure that out by looking at the two different shell X, shell Y. But we can cover that at some point. There is, a way for you, of course, to define those directions to force a particular X, local X and local Y in the shells. But for this particular case, we're just trying to match the values, so I'm not going to worry about it too much right now. Just know that you can do it. The other thing is, what if you don't want to create surface geometry in Inventor to get this model? Can you get there from a solid? You certainly can. So I'll show you there. I've created a solid 1/2 inch thick, again 20 inch by 10 inch, and then I created a sketch, and then I used the split tools to split this into two different bodies. So you can see that split goes the whole way through that body, and in the model tree we have two different bodies. So you do want to split the body, not just the face in this case. And the reason for that, or how you get shell elements, when I go to the environments and I say Autodesk Inventor Nastran, because I have the two different bodies here, there are some additional tools, i.e. under offset surfaces, where I can say find thin bodies. This dialog comes up, says, hey, we found one or more bodies that are thin. Would you like us to generate the mid surfaces? If we say okay to that, I can see it has one of the bodies. Let me select the other one. There we go. So now it has bodies 1 and 2. And we'll say okay. We're just telling it what bodies we want it to convert. And there you go. It basically creates that surface geometry for me. You can see it added two mid-surface idealizations in the menu tree. One of the other things that you can see about it, if I just double click, you can see that it extracts the thickness from the CAD model. So because it was a 1/2 inch thick CAD body that it converted to its mid-surface or shell elements, then it extracts the thickness and populates that field, whereas us with our surface model, our original surface model, didn't have any thickness, so we had to define that. So from there, the setup would be the same, right? I would have to define a material. I'm just changing the color of what would be the mesh. We'll leave it at red and green. And if we go in mesh settings, continuous meshing at 0.5 inch, we can see, there's our two different regions. From that point, you would just add the constraints and add in the material properties, just like we did for the other example, along with the load, of course, and the result should come out exactly the same. So that's another way to do it. You can, utilize some tools here inside of Nastran to extract the mid-surface from a CAD solid body. So that's, again, just an alternate way to do it and could also be useful for you. So again, I'm pretty happy with the outcomes on this one. Hopefully you enjoyed it as well and learned something new. Thanks for watching. Have a great day.